Welcome to today's webinar as a repeated webinar from last Tuesday. I'm really sorry, last Tuesday we had some technical difficulties, so this time I think this is going right, and we will record this webinar so that people who could not attend today can review the recording. So the topic is the fastest path from 3D scans to your CAD software. I'm Tobias Klein, Product Manager for EMEA and Trainer for the DACH region of Geomagic Solutions 3D Systems. What is Geomagic Solutions? So basically we were a Rapidform and Geomagic company, and as well other companies like Alibre and Sensible and so on, and they are bought by 3D Systems. So we are all part of 3D Systems, and the software division of 3D Systems is called Geomagic Solutions. 3D Systems is the leader in ideation to production, and the experience consists of former Geomagic and Rapidform developers since 1996, with more than 30,000 licenses sold. The innovation is 70 plus developers from Geomagic. We invented modern scan-to-CAD methods, have more than 30 patents on this, and 24-hour worldwide support in the USA, in Asia Pacific, and in EMEA region. And we are listed at the New York Stock Exchange with the ticker symbol DDD. Here is a selection of our customer base. So you can see there are multiple fields of industry like automotive, aerospace, consumer electronics, even research or dental, gaming. So from every industry we have customers. Today we want to talk about Geomagic Design X. So Geomagic Design X is basically a reverse engineering tool which can create parametric history trees and transform them or transfer them into the CAD application. So how does it work? We basically start with a 3D scanner. So that could be any point, a dense point cloud creation method, as a digitizer, as a maybe CMM coordinate measurement machine, or as a white light or structured light scanner, or laser scanners, ARM-based or tracker-based scanners. So any device which produces dense point clouds. And with those dense point clouds, we go to Design X. We import them into Design X and generate 3D scan data as mesh, or we work directly from the point cloud. And then based on this data, we extract features. We extract not only the shape information, we extract the parameters of those features, that is like a radius or a length or an angle. And we use that parameters to build a parametric CAD model in Design X and build a parametric dependency tree. And this complete model with the tree is transferred then to your CAD software like SolidWorks, NX, Creo, and so on. So we made a benchmark against the CAD software only with that turbo wheel example. It was modeled in a CAD software in about 12 hours. So basically it is like measuring and then modeling and measuring and modeling, a repeatable and tedious way to do it. And we did another try using a 3D scanning software, maybe like a mesh generating, and from the mesh we got some feature curves, just splines, and transported those splines into the CAD software, and using those splines we did the reverse engineering in 6 hours. And just using Design X with a scanner, scanning directly in Design X and redesigning or reconstructing this model from scan directly took just 1 hour. We have some examples here. This car was done in 5 man days completely in Design X from scan. And Ferrari car here as well, 10 hours. So tank, as you can see here, we have a tank, and there is the right track of this tank is highlighted. You can see this track consists of many pieces, so we did not reverse model the complete track. We just reverse modeled one link of this track and then patterned it around the spline and then mirrored it over to the other side. So this is a big time saver if you have CAD functionality at your hand while you're doing this reverse modeling. On the right side you can see in this small bubble a color deviation mapping. That is, while you are doing the reverse engineering, you can immediately inspect how good is your reverse modeling compared to the scan data. So you can see where are problematic zones and where is your reverse modeling in tolerance zone. In this case, there's a under structure, a beam structure for FEM analysis, an under structure for the car, maybe some steering or whatever. This was also done in 16 hours. Then some boat design, boat deck design, done in 12 hours with all those features and all information. You can see in the middle of the screen the boat is segmented into several colored regions. Those colored regions are basically areas with equal or similar curvature, and based on this equal or similar curvature we can fit geometries. We can do freeforms, we can do prismatic features like cylinders, cones, spheres, torus, whatever, and we can use those and trim the features with the remaining parts to get the final model. On this slide you can see airfoil, maybe from this time from the jet engine, but it could be also from a power generator. So also in this field of industry we are using the parametric approach. Or in building design, in this case it was a long range scan from a house from outside, and we took 10 hours to reconstruct the whole building. Or in this case, bigger plants like oil and gas plants, in this case you get all the piping, all the vessels, the beams parametric, so you can also use a pattern copy. For example, if you have just one beam and you need it 4 or 5 times in a row, then you can just use the pattern copy, so to save time. But also we can do heavy freeform work. In this case it was a mold for a gas mask, so a new product design from an old mold in this case. So basically we took both sides of the mold and then got the freeform shape and then created the whole new product from it in 12 hours. Or in this case, just mold manufacturing. This is the opposite way. If you have the product, you can reverse the product shape and generate a molding cavity from it. This was another sample for assembly. So for example, we got this complete foot of lawnmower, or leaf blower in this case, leaf blower, and yeah, we took it apart and we scanned every piece of it and then reverse modeled it, and in Design X we could check whether it fits together again. Get the interfaces between the upper and the lower part correct, and then transform it to Pro Engineer in the live transfer. Okay, now let's have a look at a live demonstration. I will start with a fan blade. So in this case, this is just the scan data. As you can see here, when I switch to the point display mode, you can see this is a dense scan data with triangles. So it's basically a triangle mesh. And based on this partial scan, it's not the complete fan, it's just one blade, we will generate the complete fan from this model. And to do that, first I will check the model for separate regions. So I can do that using this feature segmentation. This is to check for regions with equal or similar curvature, like this cylinder area here, or like this freeform of the blade here, or the plane on top of this hub. And so those different regions will be separated and colored in different color. And you can use those regions to extract, for example, for the cylinder, you can extract the axis. For freeform shape, you can fit a surface onto it. For the plane, maybe you can create a sketch on that plane to extrude something, and so on. So basically the software is like a CAD package. We can do the reverse modeling directly on the scan data, but we don't need to work every time directly on the scan data. So we can detach from scan data and work in the free space just without scan data as well. So it's good for redesigning or reinventing some already existing parts. So in this case, let's have a look at the region groups. So we can turn another color option here, and in this case the color is orange, for example, for cylinders. So I will use those cylinders and merge the three regions to get a cylinder, because we need those axes. Then we have planes here. Every blue entity is a plane. Actually, in this case, the number of points is too small to correctly recognize that this is not a plane, but it will be just merged into the other area like this one. And then we have it as part of the freeform, or you can just omit this one and then just use the freeform and just cut it with the outline and so on. So in this case, basically we have, I think that belongs together. So maybe this one and merge it. So now we have this nice freeform, and this one as well, maybe. Okay, now it says it's a freeform, and that's it for the beginning. So now we want to focus on the easy part first. The hub is the easy part. I'm not considering the plastic technology, plastic molding technology right now. I'm just considering the part itself. So we will just make a revolving body. But it's possible later we can do some shape splitting and some drafting. So in this case, just do the revolving using a section through this hub, and then we need a circular section. We need a section at the position where we can actually get the whole profile. So if we cut it, for example, on this side, then we cut through this beam inside here. So we will not get the complete section. So we need to move it a little bit to get a more complete section in this case. Okay. And now a top-down construction is quite easy. I'm just doing boxes, just simple boxes, and snap them on this area. Leave that a little bit over the center because we will trim everything at the center line. I'm getting my center line into the sketch, making it to the construction line, and then get the power trim function to trim off the remaining part. So same thing will happen with all the other things which are revolutions, like this one or like this one. So I can just snap this box to the line from the scan data, just snap, and then I can just use the power trim to trim away all these features which I don't need in this case. So this, then maybe we have a center diameter, so I just define a center axis like this. Okay, so basically this is it, and the outer area is a little bit shorter, so I will remove a little bit here as well, like this, and again trim away. Again trim away this stuff, and then again like this. And snap here maybe. And now we can have a corner trim from that line to that line, and remove this one. And we can have another box like this. Snap it here again. I'll trim away this one and get the corner trim from there to there. So that's basically quite fast reconstruction of this center area. We care about details later. And now I can just create the revolution body. So this is my hub now. Now I have a base for this fan. Okay, so what about the fan blade? The fan blade is a freeform, so I will use a freeform draping method, which is called mesh fit. We are fitting a surface on top of that mesh based on a plane which we from which we drape that freeform. And we have two methods. We have a method by allowable deviation, so I can specify a certain deviation I want to be within 0.1 millimeter, or I can say I want to have a certain number of control points which beautifies the surface. So I need a design surface, then I use this one. I need a fitting surface, a best fit surface, and I use the other one. So in this case we can also extend the surface or reorient the complete draping direction to get a nicer flow of UV lines. Here you can see the UV lines. So now the deviation analysis is important in this case. So you can see at any time of the modeling, you can see your reverse modeling is within the tolerance or not. And in next step you can pick those lines and just move them around. So you can move this line around to here maybe. And then move this line around to here maybe. And then introduce a new line in the middle. Just by control dragging, we get a new line here. And just by control dragging to here, we get a new line here as well. So we can increase the accuracy just by moving those lines and introducing new lines. So those lines are the fitting lines. Okay, better now. Now this is the first surface, so I could do the opposite way, the opposite surface at the same time, in the same manner. But I'm using, in this case, I'm using offset surface, so I could say I will shift my surface down and I want to inspect against that lower surface. And you can see the more I increase the offset, the more we go to the opposite side. Two millimeter. Okay, wrong direction. So that is the benefit of the parameters. You can enter these properties again, go into the parameters and change the direction. And now you can see, okay, we are in the green area again. So now it would be maybe a little bit larger than 2 millimeter. So 2.25 maybe. So this is the middle of the tolerance. It's not exactly the same surface, but in this case an offset will do. So we have now the upper and the lower plane, and now we need to get the outline. So I will use this front plane, and as we did before with the section, we can do here as well, but if we get only a section, then we get not a complete outline. So we have another function which is called silhouette. So we can set up a silhouette range, and everything which is in that silhouette, with everything which is in that volume, will be projected down to the sketching plane. So we have the complete outline of this pen plane. So in this case, it looks like this. In this case, we can just reuse our outline of the hub, and we can just create a spline by clicking elements on this scan section or scan silhouette, and then we can check with the accuracy analyzer the deviation. Increasing the vector multiplier increases this, like a looking glass, increases the deviation visually, so we can see it, and I can introduce more points or less points, or can manipulate single points to reflect a better fitting in this case. And then I will extend those points a little bit, extend this line, make this one a little bit smaller, this circle, because we want to be inside. So let's take this away. Let's take just this and this edge into my sketch. So we have a reference edge on the outside and on the inside, and get this as a construction geometry. From this reference sketch we can create one line in the middle, so we stay inside the wall for the overlapping region, and then we can just use power trim and trim away this part, and with corner trim we can just with power trim we can just trim away this part. So now we have only the blade outline. Okay, so with that blade outline we create another solid. So this solid is going through the whole blade, but we don't want to merge it to the main body. So in this case we want to cut it by the upper and the lower surface. So let's just use cut function, and now I can select both surfaces as tools, and I can select this one as the target body, and what I need is just the blade. Okay, so we have the blade now, and we have the hub now, and we can do a pattern 3 times about 360 degree around that axis. Now we have base of this fan. Now it's just some filleting and maybe some adding some features. Inside we have some beams, so we could do those beams as well. Let's see this one. Just create a mesh sketch over here. Now I can see my first sketch, this one, and I can reuse those lines as a reference. Make them a construction geometry, and then I can start doing this inner stuff. So now it would be useful to have the fillet first, because here we are peeking out that out of that area, but it's not a problem now because we have a little bit more material here. So in this case I want to get rid of this edge as well, so I'm using power trim. Again, trim this. Okay. And now we give this one a thickness, so we just extrude it to both sides like 1 millimeter. Okay. And then we use pattern again. So we can use this and 6 times about this rotation axis. So that's it, and then I can use a Boolean function. So the Boolean function combines all those, with the merge operation, it combines all those solid bodies to just one single solid body. Now I can start doing some features like fillets. So in this case I can just click the edge, and then I just click estimate radius from mesh, and it's automatically measuring on the scan data the fillet size. So this fillet is a little bit deformed, so you can see here we are in the green area, here is a little bit bigger. So I can say 4.7, yeah, whatever, it should be 5 maybe. Now we can see in the inner side we need another fillet as well. Let's make it 2 millimeter. Okay, and here we need some slot again, so we could do a mesh sketch in this area as well using a silhouette. Then we can get this slot shape. So here we have our construction line, and here we have our slot. Okay. That's just it. Cut it out. Okay, and this is the fan. Okay, I would go on with another model if there are no questions right now. What about the bottle? Okay, there is one question. Okay, let's see one special feature. For example, like this thread here in the upper level of this bottle. I mean, the bottle is basically a revolution, and basically some cuts in here. We could do that, but I will start with that complex part here in the first time. So I will generate my my axis between those two planes here, and I will choose one plane from which I start with my revolving sketch on this side. So I can do that base for the helix first. So this is my revolving sketch. So basically it's a center axis again, and basically it's a rectangle or something similar. So I can trim away the remaining part with power trim, extend a little bit until here. So it has some more features, but I will focus on this helix part here. So, sketch has an open profile. I should have noticed that here. Okay. So revolve this sketch, and now we have the base. Okay. Now again, I want to see my sketch, and I will create the shape of this thread here. And it's basically a circle. I can just pick this area here. It's basically a circle, and maybe with two tangent lines here. So there's a tangent line here. Then I need the same tangent angle on the other side, so I'm just using the mirror function. Maybe it's not exactly the same, but that could be also scan error or something, or maybe the bottle is deformed. So let's do like this, and cut away the power trim, cut away this part, and then maybe just close, just a straight close here to be a little bit inside that base. Okay, and now we want to do that helix. So the helix is basically a insert modeling feature helix. Well, the helix is basically a spline, a 3D spline. So it will be constructed using that helix tool. We need an axis, which is this one, and we need a starting point, which is this one. And then we can draw the helix profile, the sketch profile on here, and we can see every point should match one of the ribs here. So that's 360 degrees should be on the next rib here. So we could say we have our radius here, and we have our height, and we have our pitch and number of revolutions, clockwise and counterclockwise in this case. We need a little bit extend in the opposite direction, maybe 0.1 revolution, 0.05 revolutions. Okay, and we want to extend in the opposite direction as well, a little bit more than half. So we have revolutions 0.5 maybe, 0.55. So now the height needs to be adjusted. Okay, 3.6, or let's say 2.5. 2.5. I use the comma, then it works. 0.55. Something like that. It needs to be a little bit more. It needs to be maybe 3. So now it works. This is our helix, and we can use this helix to generate the body using a sweep function. So we just need a profile, which is this one, and a path, which is the helix. And now it goes around, but we need to specify the axis as well. So now this is the helix part, and we can use circular pattern for this object, get two pieces around that axis. And now maybe we can also draft this angle a bit inward and get the radius a little bit thinner or something like that. So that's basically that helix part. And now we will just go on with questions. Maybe I will show you something on this part as well. So I got a question about pipe modeling process. Actually, this helix part is quite similar like a pipe modeling process. So pipe modeling, we just extract the pipe if it's more than 180 degree of the diameter visible. Then we just extract the pipe line. This is similar like this helix flow, and then we just use the sweep function to generate that pipe. Or we use an extrusion, and then we use a revolution to reflect a specific pull turn bend method. Okay, I will just go on and have a look at the questions. So here we will do another mesh sketch for this base body of the bottle. So the bottle is heavily deformed, so I will not use all of the features. I will just use meaningful things like this outline from here to there, or like the tangent line from here to there. And then make that tangent line fit on top of this. Make it fit a little bit like this. And I can also check the deviation here using that multiplier. Okay, it's in this case too many pockets and such things inside there, but here it should be quite okay. So we will go a little bit upward here, and then maybe snap it to here, then maybe make another like this one, maybe straight. So we can see using this deviation analysis, we can get quite near the profile. Make a tangent again, so like this. Okay, and on the bottom, again we do something like this. Put it here, and get the center line, construction line, then I'll extend this one to the center line and do a corner trim at the edge. So I need this point up here, and I can also extend this curve here. So basically this is it, what we can get for the body first. So let's do a revolution, and we can immediately merge it to the body. So this is our base for this bottle. And now there's still more features like this inset, which is a revolution feature. It's pretty easy. So I will focus on those not so easy features like this one. And yeah, there's a good way how to do it. You can use this surface and pull that up a little bit, like outside of the model, just with control dragging, and then using this plane and the mesh sketch to cut inside this feature to get a little bit of that boundaries, like this. And now I'm just creating maybe a box around it. Convert this as a middle line. Okay, I will replace the upper and lower part with arcs. So that will be an arc, and that will be an arc. Those arcs will be equal radius. Oops. Equal radius. So I'll just move it around. Okay. That will be a center line. And both arcs need to be on the center. So now we can work with corner trim, or we can just do it like this. Okay, let's get that middle point here. Now we have a symmetry. So this is symmetrical. Even though the original part is not symmetrical, we have symmetry now. It's just if you pick the middle point of that area, then you can get the symmetry. And now I will just extrude this one into the body. So, but I don't want to merge it, it's just a separate body right now. And now I want to use the second surface, the second plane here, to get the shape of the surface around here, on this area. So I can just get an arc again, this one. Let's get rid of that. What is this? This is the helix. So, and again I can use a line which goes to the center point of this circle and which goes to the center point of this circle. And a point which goes through the center of my coordinate system, through the origin. And this will be horizontal. And again I have a symmetry here. So now I have this body and I can use the cut function again with this one and cut through this target body and keep just the upper part. And now let's have a color deviation and let's see how it looks. Okay, it looks green. Looks green. Now we need some filleting on the edges. Maybe, let's say 6 millimeter. Now it looks green. That's blue, green. Okay. And some other fillets as well here. Now I can estimate the fillets from the mesh. So it says 3 millimeter, let's say 2 millimeter maybe, or 1.5 in this case. So that's better. And now I can use this one and pattern it. Okay, we need 6 pieces, and we have this rotation axis, where it is, here, 6 pieces. Okay, and now I need the base body, and I need the Boolean function again. So in this time I need the cut function. So I'm subtracting those pieces from the center, and I'm getting this one. So, but now we still have some deviations here. So we still have some deviations here, and those deviations can be addressed using a draft function. So I can roll back before the fillet, just roll back, and I want to see my original shape here, and I want to see my scan data here. So now I need a draft function to get a little bit this side a little bit sloped, and the draft function is basically working with a central plane. So I can use a plane at the position where it fits, where it is green. So let's turn on the deviation, and then just drag my plane a little bit down. So in this area 17.5 it seems to fit. And now I will do the draft using that neutral plane, and I will draft those faces opposite direction like this. And then the filleting works again, and the Boolean cut works again. So that would be the draft, and now we could do the filleting around this body using all the same fillets, maybe. Not too much. Like this. The bottle is heavily deformed. We did forget one thing. We have an inset here. So before that filleting, again the parametric comes in handy. I can just roll back before that fillet, and then I can just have a look at the bottle where this inset starts. So I can just drag this up here, this plane, and drag it up there, and I can use the split face function. So I'm using that intersection method to split the face, split the target, and as you can see here, the target is split. So now I will do the offset surface. This one will go to the inner side, let's say 0.75 maybe. Okay, that should do the trick. And now filleting again. So let's have a look at the questions. What if the mesh has holes or is incomplete? Can you repair the mesh? Yes, of course we can repair the mesh. We have hole filling algorithms and we have mesh correction algorithms. However, if you use this reverse engineering approach, it is not necessary to fill the mesh. I can show you some of the mesh filling. So for example, if this is a hole and you need to just close this hole, then you can just click fill hole, and then it's basically just closing using the surrounding curvature information. If the hole is more complex, like this one, then you have a hole filling algorithm here, hole filling function here, and you can also bridge the hole or fill it gulf-wise, so fill it a little bit like this, start from there and only fill this part of the hole and fill this part of the hole. Or if the hole is, if the piece is corrupted, so you have a negative triangle or something like that, then you can also delete those triangles using the hole filling algorithm. It's kind of painting around here. And then just deleting. Okay, and now we have some insulas, so we can just pick to delete those insulas. And then we can also bridge or fill gulf, so it's an interactive hole filling tool. And so on. If the hole is like this, it can also be filled like this. So in the middle you don't have the feature of this ridge, so there will be no ridge, but the hole is filled. If you need that feature, then you need to model it in design, in the CAD features. Okay, any more questions? So hole filling is basically also capable of filling not only single holes. If you have multiple holes or many defects in the mesh, then you can just drag and drop and it will select all the holes and you can fill all the holes. If they are not complex, then it's very easy to fill many holes at once. But if they're more complex, then it needs handwork, of course. And we have a healing wizard which is searching for mesh errors. So for example, if a mesh has some folded faces or dangling or small faces or so, then this will be detected, and with the OK button you can clean this mesh up. Get rid of non-manifolds and so on. What is also possible is a defeature. So if you need the mesh but without this button-shaped circle, then you can just use that defeature function, and you can just select this area maybe like this and just get rid of this feature. So it's just removed. With the surrounding curvature, it will be filled and just removed. Okay, so if there are no more questions, then